All right. So today we're gonna continue our conversation, but this time starting we're gonna start quantizing the electromagnetic field. Today and the next lecture. Today is going to be quantization electromagnetic field. Next lecture, I'm gonna try to give you a very quick, brief discussion of quantization of non-abelian gauge theories. And then whatever we do after that in the remainder of the semester is going to be a renormalized perturbation theory. All right. Good. So I had promised to post the homework yesterday, but I'll do it today. Sorry about that. Okay. So review of lecture 23. Oh, wait a second. Is it lecture 24 or 5? It's 4, right? Okay, anyway, it's lecture 24. Review of lecture 23. So what we discussed in the last lecture was we discussed decay rates and we discussed cross sections. The decay rates was a setup where there was one particle that was coming and it would just decay into a bunch of particles. This was an unstable particle. And cross section is when a bunch of particles come in and something happens and they go out. Keep in mind that these arrows I'm putting is just to guide your mind, as in like what is incoming, what is outgoing, right? But this is not, we said that in Feynman diagrams, arrows mean the direction of the flow of the charge, right? So this is just for guiding you what are the incoming and outgoing, right? The direction of the flow of charge is not this. So this is the picture that we should be thinking of, right? For the 2-to-2 scattering, we define Mandelstam variables. Mandelstam variables, variable S, so P and K come in and P prime and K prime go out. P plus K squared is S, Mandelstam S variable. So this is the center of mass energy squared. It's also called invariant mass. Do you guys remember why it's squared? Because P and K appear in M amplitude. We're interested in probability, so it's M squared, right? So what will appear naturally in probabilities are square of these energies. There's a Mandelstam T variable, which is the square of the 4 momentum transfer is K prime minus K squared, right? These are 4 vectors. And then U is P prime minus K squared. This discussion is very 4-dimensional. All right. Good. Do think, for instance, if you want to know, think a little bit more about this. How does the picture of scattering is very different in 1+1 dimensions. That is one of the interesting things about 1+1 dimensions, that scattering is somewhat trivial. Anyway, that's why we have integrable quantum field theories in 1+1, blah, blah, blah. All right. So then we said, based on those variables, we can define the S channel, T channel, and U channel. So for instance, if there is a 3-level vertex here, which is 2 of these guys are interacting with some mediating particle, like say, for example, scalar in Yukawa theory. This particle can propagate this way, or this way. And we call this the S channel, T channel, and U channel, because as you switch this to this, the S variable goes to T variable. And, like this is just a relabeling. Going from here to here is a relabeling of what is meant by P prime, and K prime, right? All right, so then we discussed what we define cross-section. We said cross-section is the number of scattering events with fixed final states. So scattering is, sorry, I said cross-section. So we want to say a bunch of particles come in, a bunch of particles go out, right? We say cross-section for this incoming particles going to those outgoing particles. So the outgoing particles are fixed final states, is defined the following way. The total number of scattering events divided by rho of A, rho of B, L of A, L of B, and the area of the overlap. So what is the story? What we have is 2 beams, beam of particle rho A's, particle A's, beam of particle B. So for instance, one way to imagine this, and then the beams have an overlap with some surface area A, right? So clearly the total number of scattering events is proportional to A, is proportional to the density of particles B, proportional to density of particles A, length of beam A, length of beam B, right? That's why we divide by these numbers so that we get, we define cross-section, right? So we define differential cross-section. This is when we say what is the cross-section for when the outgoing particles, the n, for example, let's say the decay, the outgoing final states are P1 to Pn, right? So this is for infinitesimal range of P1, infinitesimal range of P2, and so on and so forth. What is this cross-section, right? So if you integrate this over this differential cross-section over all the final momenta, you get the total cross-section, right? Notice that these are outgoing momenta. They are on shell, so they're not independent. Well, sorry, they are on shell and they're not independent, meaning that there are conservation laws, right? So if you fix your initial states, the final, if you fix the initial momenta, if the final momenta have to add up to the initial momenta, that's conservation momenta, right? We saw that, for example, in 2-to-2 scattering and 3+1 dimension, that leaves us two variables, theta and phi, for instance, for differential cross-section. And in that case, the differential cross-section could be thought of as this is the angle differential element on the S2, right? Scattering sphere. All right. We wrote down the cross-section as an integral over final momenta, right? These, if you recall, these are Lorentz invariant momentum integrals, right? So these are those measures that are, this is a notation I introduced, if you recall. So for example, 2 pi to the power of 3 to P0, right? These are those guys. So removing this bit is like the differential cross-section. The amplitude squared, this is the amplitude of PA, PB going to a selection of final momenta, say P1 to Pn, but these are, I'm labeling them by F, F is final. Then there is if the initial states that you prepared had, instead of having fixed momentum, they had a wave function of particular momentum. So here is the particular incoming wave function of A particles, incoming wave function of B particles. Here is the conservation of momentum that we just put in by hand, and you have to integrate over incoming because these are wave packets. We saw that in this whole story, there is VA minus VB that comes out. This is just something that I coded, but I pointed you guys to go read about this in Peskin-Schroeder, right? So this is the important part. This tells you that total cross-section depends on the velocity, right? The relative velocity of the two beams. That is not surprising, right? Just think about the velocity being 0, right? That should be, there should be no scattering, right? So, okay, good. We defined and discussed that in the previous lecture. We defined decay rates for one unstable particle decaying to a bunch of final states, and this is the number of decays per unit time per unit particle present, right? Say particle A is decaying, it's the number of decays per unit time per unit particle A. You could decay to all sorts of different particles, right? So to each of those guys, there's a decay rate associated. These are called channels. We call these decay channels. So there is a total decay rate corresponding to all channels. And the inverse of that is the lifetime of your unstable particle, right? Then we said that the propagator for an unstable particle is like, well, if it's a scalar, it's 1 over p squared minus m squared plus 2im gamma, right? This is the same gamma decay rate. And because this propagator's norm of it is contributing to the cross-section, this is gonna, the cross-section is gonna look like 1 over p squared minus m squared, the whole thing squared, plus m squared over times gamma squared. That means that we previously, when we looked at the two-point function in momentum space, propagator momentum space. We said the poles of the propagator in the momentum space are physical particles, right? These unstable particles, they correspond to poles off of the real axis, and we call them resonances. They're called resonances. And the contribution to the cross-section is such that instead of giving some sort of Dirac delta function, when you plot the cross-section as a function of energy, you see these bumps. These are the resonances, and this gamma controls how fat of a bump you get, right? The width of the bump and the amplitude of the bump. The smaller the decay rate is, the more stable the particle is, the sharper this peak is, right? So if the particle is very short-lived, like Higgs or something very, very short-lived, right? Its lifetime is very, very small. Its decay rate, this gamma is very, very large, which means that these bumps are very, very fat. So they're very hard to detect, right? So it's hard to detect short-living particles in data. Good. Any questions about this? This is what we went over last time.
So, but in none of the theories we've looked at so far, we have these imaginary or these complex poles yet, right?
No, yeah, exactly.
Like we haven't seen a theory with unstable particles yet, because that's
Correct.
like an interactive theory.
Correct. So that the first example of such things will you will see in part 2 of the course when we discuss spontaneous symmetry breaking. So can you guys name some massive particles in standard model in nature? What are the massive particles that we deal with? Say boson.
It's like the WZ bosons,
Correct.
for example.
Yeah, W plus, W minus, and Z bosons are massive bosons, and they come out of spontaneous symmetry breaking. So they are unstable particles, but we haven't said anything about that. But they are out there in nature, right? All right, good. Any other questions? All right, so now today we're going to talk about we're going to start a new section, part of the course, and we're going to discuss quantization of gauge fields. Previously, what I gave you was I gave you some basic rules for like what is the propagator for a photon, and I just told you what it is, right? And some gauge, and I talked about certain aspects of like gauge invariance and how it's tricky. We talked about word identities as consequences of symmetry, and we talked about the incoming and outgoing states of a photon given by these epsilon mu and epsilon mu, which were basically polarization vectors. So today we're going to discuss all of that, derive that systematically. The next lecture, we're going to generalize this to non-abelian gauge theories, but I'm not going to go too far in depth into that because the full story is pretty complex. And then we're going to get to perturbative renormalization. All right. So recall what the gauge theory was. Gauge theories were theories with special form of non-local observables. So these theories are non-local. These non-local observables were called Wilson loops, right? If you recall, there's like, there's a particular type of non-locality in them. Insisting on a local description led to the introduction of gauge field, which had unphysical degrees of freedom, right? This theory is not local. If you insist on a local, you could make it local by introducing some ad hoc made up degrees of freedom, unphysical degrees of freedom, right? The simplest example of this is electrodynamics. This is a U1 gauge theory, right? And chromodynamics is SUN gauge theory. Chromodynamics is the theory of quarks, right? Good. Any questions? So today we're going to talk about U1 gauge theory. And next lecture, we're going to talk about SUN gauge theory. All right. just also recall there was a geometric picture that was underlying all of this gauge theory business. That geometric picture, I always find it to be very intuitive. So what was the story? You have a space-time manifold. A scalar field was just a function defined, say real scalar field is a function defined at any point on space-time. You could think of that function, if it's a real function, you could think of that as some fiber bundle, which is space. At each point, there's a line, R. And the value of the field is a point on this line, right? So more generally, if the field is a vector field, right, then what you have at every point is like some, say it's a group, right? It's a group. There's a group G at every point, and your vector is, your field is some vector at any point. Now, what is important is that now to write, we want to write an action that's local. The local action will be dependent on not just the value of the field, but also its derivatives. You have to define derivative. You have to have a way of comparing this vector at this point to this vector at this point. In the case of scalar, that's pretty straightforward. But in the case of when you have these like these fibers, then it's no longer clear how to do this, and any particular choice corresponds to a choice of a connection. We need the notion of a connection. We argued for that, right? So, for example, if phi A is your vector field here, you define phi of A x mu plus epsilon mu, x mu plus epsilon mu moves you along M, space-time, this is M, right? It's phi A x mu plus epsilon mu del AB del mu phi B plus some matrix, right? This is a choice of a connection. And then we call this a covariant derivative, right? Then we said field strength is the curvature of this connection. So it's basically the covariant derivative of A mu anti-symmetrized. So the covariant derivative setting the covariant derivative of a function equal to 0 gave us parallel transport, right? That was a notion of how to take a vector and move it along some path in space-time, right? That was parallel transport. So this was the geometry of gauge theory. Just wanted to remind you guys of this. Are there any questions about this part? Okay. So the gauge field is really just a choice of a connection, right? It's Lie algebra valued, right? Okay, so the gauge theory Lagrangian that we wrote down was -1/4 trace of F mu nu. This trace is over the representation matrices, right? A and B. So, and this that 1/4, there could be a number down here that was actually related to this dimension of the related to the representation as well, right? So I'm being a little bit schematic here. So this was called the Yang-Mills Lagrangian for the case that the gauge group was SUN. The simplest case to consider is U1 gauge theory. It's a theory of electromagnetism, right? So let's recall how that worked. In undergrad physics, you describe electromagnetism in terms of the electric field and the vector field. Then you define the vector potential A and electric potential phi, right? That are related in this fall using these equations to electric and magnetic field. Once you learn about relativity, you put them together as a 4-vector. Phi is just a 0. This is a 4-vector potential, right? And then you define F mu nu as the anti-symmetrized derivative of this guy, right? So this F mu nu is anti-symmetric. So as a matrix, it has zero I elements. It's just electric field, and its ij elements are just some epsilon ij of the magnetic field. So this is just this F mu nu is a compact way of writing the electric and magnetic field. Good. It's a 4x4 anti-symmetric tensor matrix, so it has 6 degrees of freedom. And it's electric and magnetic field. We wrote that down explicitly. Now, Maxwell equations, we wrote them down in this particular way, right? They became del mu of f mu nu is J nu. J is are the sources, right? So Ji are current densities, and rho, J0 is charge density, right? And if you take del mu, if you take del nu of this equation, left side and right side, because this is anti-symmetric and del mu and del nu commute, the left side will vanish, which will tell you that del nu of J nu is 0, and that's called current conservation. Good? So that's conservation of current. Any questions? It's a good point if you have any questions. So I'm just reviewing the Maxwell theory, electromagnets. Now, this 4-vector potential, mu, has redundancies. These are gauge redundancies. Under a gauge transformation, when we shift mu by derivative of an arbitrary function of space-time, you learn that f mu nu is unchanged, right? Which means that this term in the Lagrange is unchanged. Now, you could ask what happens to this term in the coupling to a source. Is it clear why this is gauge invariant? We worked this out explicitly. It's just because this has del mu. Gauge field f mu nu is like del mu a nu minus del nu a mu, right? The contribution of this term is going to be del nu alpha, del mu alpha, del mu, right? So they commute and cancel. All right. However, in non-abelian case, if you recall, f mu nu was no longer gauge invariant, but f mu nu, contracted indices, trace of it was gauge invariant. All right. So under a gauge transformation, this term is invariant, but this term changes. It changes by the following two terms: del mu of J mu alpha, del mu minus del mu of J nu alpha. So I've done integration by parts. This term vanishes by current conservation of current, right? We saw that this is always 0. This is a total derivative term. When we integrate it in the action, it goes all the way to the boundary, and if the gauge transformation is 0 all the way to infinity, for instance, it just vanishes, right? So the full action is gauge invariant up to the, well, yeah. That instantly tells you that you're going to have, this is just an advanced comment. If you have large gauge transformations, these are gauge transformations where alpha doesn't vanish at infinity, right? The action is not invariant under those transformations. So that's a long story in gravity, that's a long story in QED, QCD, all of that. So if you ever hear the terminology of large gauge transformation, that's what it means. But we're not talking about that for now. We're always requiring things to vanish all the way. So here's our action. I just explicitly expand f mu nu. There's minus half del mu a nu, plus half del mu a nu, right? Plus j mu a nu. So by integration by parts, you can write it in this way. So if this should be familiar, if you recall, for a scalar field, sorry, there's no equal. For a scalar field, when we start with this action, we did integration by parts to write it as this, right? Plus a boundary term. And we saw this was the thing that when you path integrate over phi, right? It becomes the inverse of it as a propagator, right? Because you have to complete the square by shifting. If you have a Gaussian integral, you have to complete the square, you shift by the inverse of this, and blah, blah, blah. We did that before. So we're just repeating the same procedure. there is a term that comes out that's a total derivative. All right. So now this is a Lagrangian. It's pretty clear how to get the equations of motion out of this. You just vary this Lagrangian with respect to a mu, for instance. Right? So the action, what comes out is this term, a, and this term. So you end up with these equations of motion. Again, you realize instantly that this is just del nu f mu nu. Right? So this is just Maxwell equations. Now, here is something very important. In the action, because your f mu nu is antisymmetric, a nu del zero of a zero is there. It does not appear in the action, right? Because it has to be antisymmetric. So a zero, the time derivatives of a zero are not in the action. So a zero is like imagine we wanted to start quantum field theory with an action that was something like this. It was, for example, del I phi minus half, no time derivatives. Such a theory doesn't have dynamics. Such a theory is that's just constraint. You just have a constraint to satisfy. There are no time derivatives of a0. There are no canonical conjugate momenta associated with it. So there's no dynamics associated with a0. We saw that when we quantized in the last lecture, I commented on this, that there are all sorts of problems that come up. These a0 modes seem to create negative norm states. And then I claim that, oh, it won't matter because it doesn't couple to anything, it just goes for the right. It's non-dynamical. It's just a constraint. To eliminate gauge degrees of freedom, we often choose a gauge. So convenient choices of gauge are something like this. We could pick a vector in space-time n mu and require a mu to be perpendicular to that vector. If what you pick is space-like, this is called an axial gauge. If what you pick is light-like, that's called light cone gauge. If it's time-like, it's called temporal gauge. Two other famous choices are the Lorentz gauge and the Coulomb gauge. We'll discuss these two choices here. We could quantize the gauge theory using any of these choices. When you quantize gauge theory with different choices, the theory that you obtain is equivalent, but the form of the propagator might look a little bit different in all of them. But it's still, again, everything is taken care of in such a way that it's all nice and good, because you're picking different gauges, right? Not everything in a mu is physical. So today we're going to talk about these two choices. The Lorentz gauge is covariant, right? It's very nice and it's convenient to work with. The Coulomb gauge treats space and time differently and is convenient to relate it to canonical quantization. So in canonical quantization, Coulomb gauge is more intuitive. And path integrals, if you want to stay covariant, Lorentz gauge is more intuitive. We'll discuss both of them, starting with the Coulomb gauge, and then at the end, today we're gonna talk about the Lorentz gauge. So what I'm gonna do, the remainder, is I'm gonna pick Coulomb gauge, do canonical quantization, describe everything. Then in the leftover time, I'm gonna pick the Lorentz gauge and do path integral quantization. Is that good? And I hopefully explain my choices. There's no, you could pick Lorentz gauge and do canonical quantization. No big deal. It's just that you would be carrying extra terms that are annoying because there's no physics associated with gauge. We will actually say later in the next lecture, if there's time. I don't know how deep I'm gonna get into non-commutative theories. Sorry, non-abelian gauge theories, but there is a way of doing it in a fully manifestly gauge invariant way. That's the Fediev-Popov method, and it's very convenient, but it comes at some cost, right? We'll see that. The cost is that you will have these negative norm states just all over the place, right? Those negative norm states, they're called ghosts If you ever hear the word ghost in particle theoretical high energy physics, that's what it means, right? This is just an artifact of the fact that we are insisting on some made up degrees of freedom, right? It's just not there. These are redundancies. We are calculating, we're summing things redundantly, and the role of these negative norm states is just to take care of these redundancies, just divide by the redundancies, right? There's no physics associated with them. You can't excite them. They're just like part of the formalism that will make sure that the final result that you get is properly normalized. That's all. Good. Any questions about what we're going to do? So in the remainder of this lecture, we're going to do Coulomb gauge quantization, canonical quantization. Then I'm going to comment on Lorentz gauge and path integrals. So electromagnetism in Coulomb gauge. To impose Coulomb gauge, we apply the following projection. I discussed this previously in lecture 9, 10, whatever it was. You take AI of x, right? This is the vector potential, 3 vector potential, and act on it with this projection. This projection basically makes sure that del I AI is 0. This projection, what it does is that it takes the vector k. So if you fully transform this, what it does is that it takes a vector ki and removes the elements of aj in the direction of ki. Right? Because if I Fourier transform this, I get ki ai equal to 0. Right? ai is a 3 vector. It will have a momentum 3 vector. So we say that we always choose ai as a 3 vector to be perpendicular, orthogonal to the direction of ki. Right? That's why ai as a vector ends up with 2 degrees of freedom. Right? Those are the 2 polarizations of the field. Is that clear? We'll go through this in more detail, right? So in Fourier space, ai of k is basically this. This is I'm summing over these indices, right? Good. So, all right, that is the prescription. That's the projection we're going to do. Our vector potential is phi ai. Let's just take the Lagrangian, and every time we have ai, just put next to it this guy inside the Lagrangian. So what you get is half ai dot squared minus half del j ai plus j I ai. This whole first line describes the dynamics of a 3 vector field. Right? This last line describes the physics of the A0, the gauge potential. As I commented before, it has no time derivative. So this just, the whole thing is a constraint. This is super boring. This middle term is a little bit different. The quick summary is that the middle term goes away. Why? Well, the end of this is half del I aj del j ai plus ai dot del I phi, right? Let's do integration by parts. Integration by parts will bring this del I on this side, gives us a boundary term. That boundary term vanishes. Then del I ai has to be 0 by our gauge condition. So in this gauge, this term goes away. Similarly, by integration by parts, I bring this del I next behind this guy. Again, by our gauge condition, this term goes away as well. So we end up with the following Lagrangian. There is this dynamics for a 3 vector field, dynamical 3 vector field, coupled to conserve current, Ji as a vector, 3 vector. And there is this like electric potential that just decouples from everything. It doesn't have any dynamics. There are no time derivatives. So let's first solve the dynamics of this. Solve the equations of motion for this phi. There's no dynamics associated with it. So what is the equation of motion? The equation of motion says that you just vary this guy with respect to phi. So rho is minus nabla squared, right? This is called the Poisson equation. There's no dynamics in it. You tell me what rho is in space-time, I solve for phi. This is what we're doing in electrostatic, right? And physics 101, 102, they were describing to you where the charges are, and you would just solve their addressed, and you would solve for the electric potential everywhere, right? There's no dynamics, nothing is evolving. There's no data to that you need to describe that things evolve, right? This is it. This is it, right? What is the answer to this? You just integrate this, the answer to the unique answer to the solution to Poisson equation. If the charges, if the charges vanish all the way at infinity, and the field, the scalar potential vanishes all the way at infinity, that's just a normalization choice. It's just this, right? You take your rho, integrate it over space-time with x minus y. Hopefully this is like very familiar from electrostatic, right?
Just to clarify, so when we like solve for phi here, it's not like a retarded potential, right? Like causality is taken care of by shoving everything onto A, right?
Yes, absolutely. There's no
Okay.
dynamics. Retarded has to do with dynamics, right? There's absolutely no dynamics here.
Yeah. So all of that, all like causality is shoved onto A essentially. Like
Yeah,
A takes care of all that.
Exactly. Exactly. Now, okay, so oops, we solved this. It doesn't couple to anything. It doesn't have any dynamics, which means that we could just plug this solution. It's always on shell in a sense, like you can plug this solution directly into the Lagrangian. So you had your Lagrangian for the dynamical vector field, three-vector field, and you get an extra term in the Lagrangian that's called Coulomb term. It's just you describe to me what the rhos are, what the distribution of charges are in space-time, and that contributes a fixed amount, a fixed constant to a fixed amount of the Lagrangian at any point in space-time, right? So for instance, in canonical quantization, in a second, we're just going to calculate the Hamiltonian. This is just like a shift. It says that there is a term in the Hamiltonian due to the energy of charges. That's it. And this term is not related to the dynamical degrees of freedom, which is the electric and magnetic field. Good. So let's do that. Actually, okay, good. I'm on time. Oh, sorry. Yeah, let me pause here. Is this whole thing clear? So in this Coulomb gauge that we're dealing with, hopefully it's clear that there are only 2 degrees of freedom left, right? A0 is a constraint. There's no dynamics associated with it. It just goes for the right. The negative norm states we found was because it was something silly. We were quantizing a constraint, something that was non-dynamical, right? There's no sense that it could go off shell or anything. So that's why we got those negative norm states, and that's why they're unrelated, right? And here you see explicitly that the A0 phi just decouples, right? It completely decouples from the degrees of freedom. It just it gives you some overall. It's fixed by your sources. You have 3 degrees of freedom in your vector field, and those 3 degrees of freedom, you still have a gauge condition. You have to gauge fixing. In Coulomb gauge, you fix it to be perpendicular, your A vector to be perpendicular to the direction of the K vector, right? So that leaves 2 degrees of freedom. And those are the 2 helicities. Those are the 2, polarizations of the photon. Good. We discussed this in detail why a massless vector field, right, has 2 degrees of freedom. This had to do with the representation theory of Lorentz group, right? We talked about helicities, all of that, right? Good. Actually, here's a good point to say. The distinction, I could redo all of this instead of instead of Coulomb gauge, which was this, instead of Coulomb gauge, which was this, I could pick the Lorentz gauge. How does the story change? Well, it doesn't change much, but what happens is the following. Your 2 degrees of freedom end up being the following. You have a 4 vector for your propagation, right? And you look at the space, you take your A mu to be in the perpendicular directions to this 4 vector. So that's 3 degrees of freedom. And then out of those 3 degrees of freedom, one of them is a constraint, is unphysical, right? Good. This is just for in anticipation for what where we're going, right? So for example, if you have a photon, if you have a particle, a vector field propagating, right, with momentum k in this direction, the vector field also has like 3 elements in 3-dimensional space, right? But if it's massless, there is no sense in which it can have an element in the k direction. It has to always be in the 2-dimensional perpendicular directions. So this object we defined here is the projection. This AJ that we started with, we pretend it's a 3 vector. It's not a 3 vector, right? You have to project it down to the perpendicular direction. So when I started here, my initial AI was some vector like this, and that projection just projects this guy down here. Good. Clear? All right. So let's do canonical quantization. Varying, now let's focus on this term. So we discussed the Coulomb term. Let's now quantize these degrees of freedom. Right? So it's a 3 vector. It's massless. Naively, you might think that it has 3 degrees of freedom. We'll see it's 2. And I already commented about that a few times. As you vary A mu, you get the following equation. Del squared of A mu of x is del ij minus del j over del squared j I of x. So in the previous lecture, well, actually, no, let me not comment. All right, so this is your equation of motion. This instantly tells you that not only A mu cannot have any elements in the direction of a propagation k vector, but also j cannot have an element. Because if you just Fourier transform this, you learn that k mu, ki, ji has to vanish. I gave that, there's a covariant version of that. We'll see in a second. J mu, k mu has to vanish. I gave that a name. What did I call it? I call it a ward identity. That's what the ward identity was. Okay, so let's pick a simple setup where j is 0. So we're dealing with del minus del squared of ai is 0. The solution to that, keeping in mind that we want del I ai to be equal to 0, could be expanded in the following way. It's the sum over lambda plus and minus. These are the 2 different independent degrees of freedom. These are the polarizations of the photon, right? I'll explain in a second. Integral, this is the good old integral over the Lorentz invariant thing. Lorentz invariant integral measure. Epsilon lambda, this is a vector. It's a 3 vector, because this is a 3 vector. Star of k, a lambda of k, e to the power of I kx, plus epsilon lambda vector of k, a lambda dagger of k, e to minus I kx. Here, A and A dagger are going to become the creation annihilation operators. Annihilation creation operators for photons. Now, what are these polarization 3 vectors? These are 3 vectors, but as we said, our gauge condition requires that k vector is perpendicular to E lambda of k. So there are only 2 degrees of freedom left. One convention is, for instance, take the degree of the propagation of k to be in the kz direction. Then you have the X and Y. And a convention that's nice is right-handed polarization is this vector, 1 minus I, and left-handed polarization is 1 plus I. Two independent vectors, right? These polarization choices are more canonically understandable when you write down the Lorentz representation theory, right? We talked about the little group and all of that. This is that story. All right. So hopefully I explained what the polarization vector is. So previously when I told you guys about final diagram rules for QED. I said for any ingoing particle, you put epsilon of lambda of k e to minus kx. And for every outgoing, you put e to the power of ikx epsilon star of k. This is where it comes from. This lambda are the polarizations, right? I always summed over polarizations. Good. All right. So of course, they form an orthonormal basis for vectors that are projected by this. So that's pretty straightforward, right? So there are these two guys are orthonormal with the choices I wrote down. And once you take the inner product of it, it's just a projection to the plane perpendicular to K. We're left with the creation and annihilation operators with lambda being plus and minus polarizations, right? And yeah, for every momentum K, there exists one such things. So these guys create and annihilate photons with a particular polarization and particular moment. Good. So to do quantization, all you need to do is, well, you look at the Hamiltonian, right? So you take Lagrangian in very respect to AI dot, that's AI dot, so your canonical conjugate. So your Hamiltonian is half momentum squared plus del J AI del I J A minus J I AI, and then there's a Coulomb term. Forget about Coulomb term for now. It's just going to shift the vacuum energy. That's all it's going to do. So to quantize, what we want is we want to put canonical commutation relation between A as an operator and pi as an operator to be I. But of course, we want to make sure that everything is in this direction. It's perpendicular to K, right? These equations are equivalent to setting the canonical commutation relations for the standard relations for A and A dagger, right? Here, there's omega, if you recall. What is omega for a massless particle? It's just norm of the K vector. Good. Omega is just K0. Because it's massless, on-shell condition tells you omega is a norm of K. So you just do this, follow what you knew before, and what you obtain is, like you construct the Hilbert space, photons act on the vacuum, that you can create photons of different momenta, but for each momentum, you can create you have two choices of polarizations to pick, right? And the only thing I want to comment on is the Hamiltonian. So your Hamiltonian has basically a number operator for each of, it's basically the number of photons in any, for any particular polarization in any particular mode, the energy of that mode, right? Integrated over all the modes and all the polarizations, both of the polarizations, right? So it's just every photon that you create has a particular energy. So you sum over the contribution of each of them. It's just partitions of integers, right? Well, actually, it's not partitions of integers. Never mind. That was an incorrect statement. They're not all equal energy. All right. There's a vacuum energy term, right? Good old vacuum energy problem that we had before that we just pushed under the rug. There is the term that has to do with the interaction of the vector field and the current, right? The current contributes to the energy, Hamiltonian. And there is the charge, which is the zero component of current, which contributes to a very fixed, predetermined amount to the Hamiltonian. Good. You construct the Fock space a good old way, And when I was describing asymptotic states of photons, that's what I was talking about. Any questions?
I have a question about the polarization vector.
Yeah.
Earlier, when we discussed quantum electrodynamics, we said that the polarization vector is a 4-vector, and here you introduce it as a 3-vector. So, what's the difference here?
Yeah, I'll say in a second. So far,
Okay.
doing canonical quantization, which treats space and time separately, different, right? So
Yeah.
do the covariant thing. The nicer way of doing it is by going to the Lorentz gauge, right? And then over there, you're going to talk about epsilon mu, right? But it basically, it's nothing different. Well, you'll see.
Right.
It's
Okay.
really nothing different. So because I don't want to repeat myself and do canonical quantization with the other choice, I'm going to do the path integrals. So what is the path integral formalism? What we want to calculate the partition function of the U1 gauge field with a particular source J. So what we calculated for the case of spinors and for fermion, for scalar field, right? So you have to perform a path integral over a mu. I'm going to stay covariant, no splitting of space and time, right? E to the power of I, free action of a mu. All right, so what is free action of a mu? It's just minus quarter of f mu nu plus j mu a mu is integrated over space time. Good. Okay, so you repeat exactly step by step what I just did earlier. You find that it's an integral. The action is an integral over the form momentum of a mu of k squared. These are k mu, j mu nu, eta mu nu. Let me call this eta mu nu. I think I was calling it eta mu nu. Minus k mu, a nu minus k mu. Right? And then there's j mu, a mu, and then j mu, a mu. We want to perform the path integral over mu, a mu. How did we do this path integral in the case of a scalar? In this case of where scalar was, what was that? Minus del squared plus m squared phi plus j phi. If you recall, the way we did it was this. We defined, how did we do it actually? I forget. So we shifted phi by the inverse of this guy, right? There's an inverse trick. So you complete the square, right? So you wanna complete the square, write the whole thing. So you want to send phi to phi tilde, write the whole thing, this whole thing as a square, right? And then the leftover piece is j. Actually, let me do it explicitly. I'm not happy with what I just did. So let's shift phi to phi plus, let's see, what do you want to do? You want to do j over del squared plus m squared. Is that what you want to do? No, actually, the other way around. You want to do, anyway, you remember completely. It's just complete square. Let's not kill time here. I did it explicitly before, and it involves inverting this operator, inverting this guy. But now you notice that the thing you're trying to invert has 0 eigenvalues. It's a projection. Of course, projections have 0 eigenvalues, right? So they're not invertible. To see it's a projection, let's just work it out explicitly, but it's a projection to the 3-dimensional subspace that's orthogonal to k mu, right? This is just what we just did for the 3-vector done for the 4-vector. Here you're projecting to the 3 dimensions perpendicular to the dimension to k mu, right? So this is your eta mu nu minus k nu over k squared. It's a projection. What is a projection? Does anyone know what a projection is? What's the definition of a projection as a matrix, for instance?
P squared is P.
It's also self-adjoint. Yes, it's a self-adjoint matrix. That's P squared is equal to is square. That's it, right? In this case, because it's real, it's just symmetric. It's a symmetric matrix that's equal to its own square. So there we go. That's it. So you just multiply by itself and you get itself. So it is a projection. A projection, what's the spectrum of projection? 0 or 1. So the spectrum of this projection is 1, 0, 3 ones, right? So there's a three-dimensional subspace that's perpendicular, that has, sorry, P mu nu K nu is 0. That means that K nu is in the 0 eigenvector. And the three-dimensional subspace perpendicular to K nu are you pick three eigenvectors in there, any basis, your favorite basis. Those are your projections, right? On top of it,
And when we say perpendicular here, we mean Lorentz perpendicular.
correct. Yeah, the only inner
yeah,
product we
okay.
have is the Lorentzian product. Yes. K mu, J mu is also 0. That has a name. That was word identities, right? So we said that J mu also has to be perpendicular to K mu. So if we have both of these conditions, it's silly to path integrate on A mu's element in the direction of K. That's just unphysical, right? It has to be, it has to be projected out, you shouldn't path integrate over. So we do not path integrate over those directions. You sort of define in your path integral, you redefine in your path integral A mu by the projection of A mu to this three-dimensional subspace. Now your projection is just identity, so it's invertible. And here is, you do the integration by, you do the Gaussian integral. This is your Z0 of J. This is your propagator in Lorentz gauge, right? And its Fourier transform as a propagator in real space. Good. You still have a constraint, right? You still have a constraint. I haven't discussed a constraint yet. Actually, maybe here's what I should say as before. So what is the constraint? This question came up before. So now when I look at my A mu vector, I take my field, let me just explain it, sorry. When I take my A mu vector field, I project it to this subspace, right? This subspace is P mu. Oh no, that's not how I want to do it. It's basically, how do I want to do this? Eta mu nu minus del mu over the, oh, not del mu over del alpha, right? Over A mu. I have 3 degrees of freedom left. Out of those 3 degrees of freedom, one of them is a constraint, right? So if you take this guy, has 3 degrees of freedom, and try to quantize it, you're going to expand it naturally in the language of epsilon mu's, right? But these epsilon mu's, as vectors, they first satisfy, they're first living in this three-dimensional subspace, right? And the constraint gets rid of another degree of freedom, right? So for a generic K mu, what you end up with is, again, 2 vectors of this type, right? So previously what we had was, what was it? It was, let me bring it up. What I had was two, yeah, I had these two vectors. These are, I can think of these guys as epsilon mu plus minus, right? Obviously. So when you do it covariantly, you still have the same degrees of freedom, epsilon mu of lambda, two of them, right? But you can write as a 4 vector, right? Here, if I want to write as a 4 vector, it would be square root 2, 0, 1, minus 1, and 0, right? Plus minus 1. Good. Does that answer your question? It's just that way everything is more covariant. There, you're not doing any particular splitting of space-time. All right, where were we? All right, so we end up with the propagator in the Lorentz gauge, which is this in momentum space, and this is a propagator in Lorentz gauge, in the actual space. If you look at the expressions I showed you guys in the previous lecture, instead of p mu nu, I was writing eta mu nu, if you recall. For the propagator photon, I was writing here eta mu nu, but then I was explicitly also next to it was writing this condition. And I was writing k mu, all of these m mu's, the ward identities, right? So it's sort of my choice what notation I want to pick. I could put it explicitly in here, in the propagator, or I could say that, oh, my incoming and outgoing legs always have to satisfy these conditions. Good. So in summary, this is the end of this lecture. In summary, what did we do today? We started with U1 gauge theory as the simplest example of a gauge theory. It's a theory of electromagnetism. We quantized it, right? So the first thing that we noticed was that phi, which was A0, that is non-dynamical. It's irrelevant to physics. It's just a constraint. It's just a constraint. It's Gauss's law. It's Gauss's law of constraint. So you're left with 3 degrees of freedom. Because it's a massless mode, we discussed this before. In representation theory, we said it's very mathematical. In representation theory, there are only 2 options, right? But here we saw it physically. There are only 2 degrees of freedom that are physical, because if it's a massless boson propagating in direction k, it cannot have an element. It's like the vector field cannot have an element in the direction of propagation. So for k mu, you project to the perpendicular direction. If your k mu is, well, it's covariant 4 vector, this is called a Lorentz gauge. If you split space-time and take the spatial 3 vector and project perpendicularly, that would be called the Coulomb gauge. You could pick other gauges. I talked about the axial gauge, temporal gauge, and such. Those are also valid choices, right? And you could do all of that. The physics, the result of your cross-section, amplitudes, the final answer for your probabilities are always the same. We introduce these degrees of freedom, these ad hoc, made-up degrees of freedom. They go for the ride, right? You have a choice to quantize this different ways. Now, in the next lecture, when we start talking about non-abelian gauge theories, we realize that, okay, some of these tricks that we worked for U1 gauge theory get ugly, if you want to generalize. So path integrals, as usual, save us. So path integrals, of course, there's a canonical quantization way of doing all of this for non-abelian gauge theory as well. But path integrals save us in the sense that There are just these elegant Gaussian integration methods and inversion of like operators that will just formally push everything through. We'll see. I haven't quite decided how much I want to discuss non-abelian gauge theories. Non-abelian gauge theories is like 5-6 lectures on its own, right? I will probably include a little bit, and then we'll quickly move on to renormalized perturbation theory. All right. Any questions?
Earlier you mentioned that there's a gauge independent way of doing these, right?
Yeah.
Okay,
Oh.
so is there any advantage of doing that?
It's just cleaner. I said gauge independent, but let me explain that. So we're gonna see that in the next lecture. Let me actually, sorry. Yeah, let me not try to explain that now. But that I'm gonna include that in the future. But let me just say something that's important. There are two aspects to gauge independence, to U1 gauge theory. One of them was a constraint, right? Let me just explain how to do the constraint, put the constraint in systematically, right? So we're doing a path integral over dA mu, right? And I said that there's a constraint. That's a Coulomb, the Gauss's law, right? Phi 0 is non-dynamical, and I said we shouldn't path integrate over it. A way, you see, this is, nobody asked me this. So far, oops, sorry. When we're discussing path integrals, I said, oh, you have an action, you path integrate it, and you solve everything. It's possible that your theory is not defined, your solutions to classical equations of motion are not all of them are viable things. You might have constraints. You might have something like, as we have in gauge theories, right? For example, you solve some sort of differential equation. I don't know what to write here. Not norm squared, right? You're solving this differential equation, but on top of it, you have a constraint. It has to, I don't know, satisfy something like this. Otherwise, it's not right. One way of systematically including this is just put in the path integral a Dirac delta function for it. A Dirac delta functional, right? That is a sort of systematic gauge independent way of doing it, and that's Fediev-Popov, blah, 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 right? But there's a very important principle. By now, I've said this many, many times, that I say this without like, or systematically explaining it. I've been talking about constraints. I've been talking about gauge, degrees of freedom, ad hoc things, right? All of these are to be understood. There's some sort of fundamental principle here. When we talked about locality, we said there are differential equations that you solve. There's a local Lagrangian density. That local Lagrangian density will give you different equations of motion, and the solutions to equations of motion are like the path for propagation of particles, field, the dynamics of the field. But it might be that we have introduced in the field, we've introduced some made up stuff that were unphysical, and you have to add to the equations of motion some constraints. That might be a case, right? Not every solution to equation of motion that would be physical. You have to handpick them. One way to quantize such a theory is just put Dirac delta functional inside the path integral. Good. We'll see. This is the way we quantize systematically non-abelian gauge theories. One of the ways. All right. With that said, any other questions? If not, thanks so much, guys. I'm sorry that I wasn't late, but I was about to be late today. Thank you.
Thank you.
Thank you.